Welcome. In this video, we will take a look at section 8.2, the trigonometric form for complex numbers. So let's start with the definition. We're going to do a little bit of graphing with these complex numbers. The graph of a complex number, a plus bi, is a vector that extends from the origin out to the point a comma b. So we'll notice that the complex axis is replacing that y-axis, and our real axis is the horizontal x-axis. So let's take a little bit to work through each of these complex numbers and graph them. Each one of these, again, is going to be a vector from the origin. So we'll do these in each different color. We'll start with A. The 3 plus 4i. That's going to be 3 along my real axis and 4 along my complex axis. So 3 in my real axis, 4 in my complex. It's going to end up here. So we'll have a vector extending to that point. Could have an arrow here, but it stops at that point, 3, 4. The second vector that we'll make is the vector of 5 minus 2i. That's 5 in my real, negative 2 in my complex. So that would be 5 to the right and negative 2 down. So that would be our vector going into the fourth quadrant. Part C, we have a vector of negative 4 plus 7i. So that's negative 4 going to the left on my horizontal axis and 7 up. So that would leave us at negative 4, 7. That would bring us up there. Negative 4 in my x direction and 7i in my vertical. And the last one is just 5i. If we just had an imaginary portion to this complex number, we'd just be going along the imaginary axis. So we'll do this one in red. 5i is just going to be coming up our y-axis up to the point of 5i. So these are some examples of some vectors that we can draw in the complex plane. The next thing that's going to be helpful for us with talking about the trigonometric form is the modulus of a complex number. So the absolute value or modulus of a complex number, z is equal to a plus bi, is the distance from the origin to the point a comma b. If the distance is denoted by r, then we would say that the modulus r is equal to the square root of a squared plus b squared. So again, we call this the modulus, and again, this is just really the measure of that vector that we've graphed. So let's take a look at a couple of the vectors that we just graphed. 5, negative 2 was in purple, and then we'll also take a look at negative 4 plus 7i, which was our green vector. And we're going to go find their modulus. So to do that again, to find the modulus, we'll call r. That is going to be equal to the square root of a squared plus b squared. So a squared is 5 squared. And then we'll do plus negative 2 is our b. We'll square that as well. So we'll have the square root of 25 plus 4, or this will be the square root of 29. So this is our modulus of our vector 5 minus 2i. We can do another example here with negative 4 plus 7i. The modulus here, r, is equal to the square root of negative 4 squared plus 7 quantity squared. So we'll have 28 plus 49. And if we add those two, looks to be 77. Actually, that would be 16, excuse me. 16 and 49. Looked a little wrong. So we have 16 and 49. If we add those together, we'll get 65. So we'll have the square root of 65. Taking a look at that number, I don't think there's any way to reduce that number at all, so we just have the square root of 65 as the modulus. All right, so this modulus r is going to be one of the components that's going to make up the complex, or the trigonometric form of our complex number. So this is a important thing that we'll want to find for each of our vectors to transform it into our new format. So we have the modulus. The next definition we'll need to kind of round out the concept here is the argument of a complex number. So the argument of a complex number, z is equal to x plus yi, is the smallest positive angle, theta, from the positive real axis to the graph of z. So essentially this is saying what is the angle theta formed by my complex number. So again, the complex number, we can write this as either z is equal to x plus yi. Another way we have written that is just z is equal to a plus bi. Same idea there. And the trigonometric form is equal to z is equal to r, that's our modulus, times cosine of theta plus I sine of theta, where r is the modulus and theta is the argument. Again, that's the angle formed by my vector. So again, when we think about theta here, theta is going to be an angle from 0 up to 360. So it's an angle in that first round of the unit circle, or the rotation of the unit circle, that's formed by our vector. All right, so with those two components, our modulus and our argument, we're ready to go and transform our complex numbers to trigonometric form. So let's start by rewriting z is equal to 4 minus 4i square root of 3 into our trigonometric form. We'll start by just taking a bit of a graph of this complex number. So if I wanted to graph 4 minus 4 square root of 3i, we could say that, again, this is our real axis, and this is our imaginary axis. And so we are going to go 4 in my real axis, and negative 4 square roots of 3 in my vertical axis. So negative 4 square roots of 3 in my vertical axis. So our vector here is formed at this point in the origin. So if we consider this is going to be our vector coming out, this has a distance of 4 and a distance of -4 square roots of 3. So there's two things that I want to go out and find. I'd like to find the modulus, that's the r, the distance of that vector, and I also want to go out and find the argument, which again is the angle theta formed by my vector. So let's start with the modulus. The modulus we can rewrite is going to be r is equal to the square root of my a, which is 4 squared, plus -4 square roots of 3 quantity squared. So we'll find the modulus first. This will give us square root of 16 plus, we'll have 16 and then times 3 if we square both components of the last part there. And then if we add 16 and 16 times 3, you'll find this to be 64. Therefore, our modulus here is just going to be 8. This shouldn't be surprising to us because right here we have a 30, 60, 90 triangle. If we look at that, that's going to have the same ratios as a 30, 60, 90, and this reference angle that we have inside will be our 60-degree angle, and this will be our 30. So this gives us some insight into what angle we have as our argument. If this is a reference angle of 60 degrees, that means this exterior angle that wraps around is going to be a total of 300 degrees. So we have our modulus and we have our argument, that's the argument, theta. And so let's rewrite this now in trigonometric form. We will have this complex number we'll call z is equal to, again, to write this, we want to start with the modulus. That's r, and that would be 8. So we'd say this is 8 times the cosine of our argument, which is 300, plus I sine of 300. And this would be the final result for our trigonometric form. Z is equal to 8 times the cosine of 300 plus I sine of 300. So again, all we need to know is the modulus, r, and the argument theta, and we can put together our trigonometric form. Let's take a look at the last problem here. We are in standard form, or we are in trigonometric form, and we'd like to write this as a standard form. So let's draw this complex form with this trigonometric graph. The modulus for our vector is 2, and it's coming at a 60-degree angle. So our modulus is 2, argument is 60, so we're in the first quadrant here. And this is of length 2. And we have a 60-degree angle. So that's our picture so far. And so we would like to go out and solve for our sides of this triangle with the 60 degrees. So Since this is 60 degrees, the short side is always half of our hypotenuse. Again, this is a 30, 60, 90. And then we'd have a square root of 3 as our imaginary side. So that would be square root of 3i. So when we write this in our standard form, we could say this is z is equal to 1 plus I times the square root of 3. And this would be the final form for, again, the standard form of that complex number. So I hope this is helpful with getting started with the trigonometric form and the standard form for our complex numbers. Look forward to seeing you in the next one. Thanks for watching.